Hi, how you guys doing? I'm good, thanks for asking. Um, Today we're gonna talk about. Oh, this is my last video too, and today we're gonna talk about how to find velocity and position function by the integration of acceleration function. So let's get started. Now, first we're gonna let a equal acceleration function. So from this information, what do we know? We know that that oops. We know that the derivative of velocity function dt v over t is equal to acceleration. So in reverse, the velocity the velocity function would be equal to the integration of the acceleration function with respect to time. Whoop. And now we simplify this. Acceleration is just a constant, so we take that out. Equal dt. This is integration sign. Sorry about that. So after that, we would get, well, integral of something of 1. Well, this is 1 right here. So integral of 1 with respect to time would be t. So we get a parentheses t plus a constant because we're taking the indefinite integral. Boom. Okay, let's give that a C1. And then we just multiply back in, so we get oops. Alright, we get AT plus AC 1. So this right here is the velocity function by integration of acceleration function Vt. Alright, let's look at an example. A ball thrown from 100 feet buildings has initial velocity of 96 feet per second. So initial would be VO, initial velocity. And from this we know that the acceleration, boom boom boom, I forgot to mention on Earth. So acceleration on Earth is constant, which is negative 32 feet per second square. Earth. Yeah, Earth. Okay, so let's find the velocity function out of this. Okay, so we know that the initial velocity is 96 feet per second. So what that basically means is that this is the velocity when times is equal to 0. So the initial velocity v0 is equal to 96 feet per second. Okay, and we know that Vt is equal to At right here, At plus AC1. So V0 can also equal to, just plug in 0 for variable t, so we get 0 plus AC1. So initial v at 0 is equal to this right here, and v0 is also equal to this right here. Okay, so now since both of these, since this equal this and that equal that, this equal to that, so it's gonna be AC, 96 feet per second equal to A c1. Okay, so to find c1, the constant, we would have 96 divided by 32. Oh, actually, it's negative 32 since it's dropping down. So acceleration is negative 32. So when you calculate that, you would get negative 3, and that would be the constant. So the velocity function that we have from integration of acceleration is v t is equal to negative 32. Oops. Negative 32t plus 96. Okay. All right. How do we get this? Well, we're basing this on this derived right here. So a, we have the negative 32 feet, negative 32, and t is the variable, it's the function that we're doing, and plus c1. Well, we know that a is negative 32 and c1 is negative 3, so negative 32 multiplied by negative 3 would get us 96, and that's how we got the answer, the function for that. And we're done with the velocity. Now let's go to the distance. So we've learned that the derivative of the placement, the position function, derivative of the position function would be the velocity function. So we have dt of st would be equal to velocity function. So in reverse again, if you were trying to find the position function, you will be taking the integral of the velocity function dt. Okay, and but we found out early on that the velocity function is equal to, so we have integration, and velocity function we found earlier is equal to negative 32 t plus 96, and we're going to integrate that with respect to time again. Oh, this plus, man. Oh, okay, that's not a plus. Oh no. Alright, that's good. Okay, now we're gonna take the integration of this right here. Well, the integration of a sum is a sum of integration, so we would break that apart. So we get this negative 32 t dt plus integrate 96 dt. And now our next step, we take negative 32 and 96 out because they're constant. Integration of constant is a constant of integration, so get integration of t with respect to t plus 96 with respect to dt. Okay, now we have, so the integral of t with respect to dt would be we still have negative 32 here. Okay, and 1 plus 1 is 2, so it's going to be t square, I believe. Yep, it's going to be t square over 2 there plus 96. This integral right here would equal to x, I mean t in this case, so it would be 96t, and indefinite integral would be plus a c constant. Okay, so if you would simplify this, you would get negative 16 t squared plus 96t plus c. Okay, and and so the next that we will be doing is we will evaluate the position function that we just find right here at time equals 0. Well, we already know the answer because earlier we said that it was thrown from 100 feet high buildings. So at time 0, the position function was at 100 feet above the ground. So S0 is 100, and at the same time we will evaluate S of 0 into this function right here. So if you evaluate S of 0 into that function, we would get 0 t squared, 0, this thing goes to 0, 96t, that thing goes to 0, so we would have c. Okay, so this thing are equal to each other, so that makes c equal to 100. So we have c equal to 100. And now we can rewrite our position function. S of t equal to negative 16 t squared plus 96t plus our new constant, which is 100. And this is our position function from the integrations of velocity and from the integration of acceleration, and we are done.